So you can see that? Don't worry about that answer being so ugly. Think about it. 9 to the 5 times the number plus 1 has to be 27 to the number minus 2. It's going to be very likely a weird-ass number to make that true. Was it difficult to get to this weird-ass number? No. Maybe. Now, some of you guys, hopefully you realize the curriculum doesn't take us far enough. What if it was 9 to this equals 26 to this? This wouldn't work worth anything. We'd have to have some other way of doing it. Unfortunately, we don't quite go that far here. So it's going to be something most of you might never worry about that, but maybe in the back of your brain, how the hell would you do that shit?
Do you mean like factoring?
You'd have to actually use logarithms to figure it out. Okay. So here's the last thing about logarithms. I'm just going to talk about some properties of logarithms. Somebody remind me, the answer to a log, what does a log always represent? A logarithm always represents a power. So a logarithm always represents a power. It's the power that the base needs to become the inside. So the properties of logarithms are the exact same properties of powers. So somebody help me out. If I add b, let's say, let me do this. Go with me for a second, like you always do. If a is b to the 5th, and c is b to the 7th, I'm writing it like this for a weird-ass little reason, you just gotta go with it. Then what is a times c? Don't overthink it. What is a?
35.
What is a?
Power.
What is a? B to the 5th. What is c? B to the 7th. So what do you get? B to the... I got 5 b's times 7 more b's. How many b's do I got in a row now? 12. Right? And people will argue with me when I first teach them this. They're like, wait, you're multiplying, and 5 times 7 is 35. Nowhere up here does it say 5 times 7. In fact, you ready for this? Nowhere up here is there a number 5. There is no 5 up there anywhere. There is none. And some of you guys are going to be like, what? But no, that's not the number 5. What does that thing mean? It means there are 5 b's. So all I see up here are a bunch of b's. I see 5 b's, and then I'm going to link another 7 b's. So of course I'm going to end up with freaking 12 b's in a row, right? So don't only memorize the properties of powers. Let them make complete sense. Make total sense if you let them. So now watch. The power on the answer. The power on the answer was the sum of the powers on each of these, right? Of course, that's what we just talked about, right? So the power, what does this represent? Oh shit, what did we just say? What's a logarithm always represent? The power. So the power on this product, shit, stay with me now, is the power on this plus the power on this. That's what it is, isn't it? 12 is 5 plus 7. Wow, Jeff, good job. Just proved 12 is 5 plus 7. Yeah. This is always true, though. The log of a product is the sum of the logs. Why does that make complete sense? What do you do with powers when you multiply things with like bases? You add them. So the log of a product is the sum of the logs. Because that's what you do with powers, and logs are freaking powers. So without doing all this shit again, what must be true about log base b of a over c? What do you do when you divide things with like bases? What do you do with the powers? Subtract them. So this would be the power on A minus the power on C. So this is all, these two things are always true. They are properties of logarithms. So what the hell good are they? That's always a great question, right? You're like, all right, whatever you say, man. shit that you use these for. Alright, real quick example. There's one more property to talk about, but I want to make sure you guys understand these two. By log base 10 of 5, can you figure that out? Log base 10 of 5. Can somebody tell me what that is? You have no idea what it is. Because what's the question asking you? What do you raise 10 to make it 5? As a human, that's really, really hard for me to figure out. I can maybe think about it forever and then come up with an estimate. Do you guys understand what I'm saying? So there's no freaking way in hell you can figure that out. What about log base 10 of 2? Same problem, right? Can you tell me what that is? I have no idea what that is. What do I raise 10 to make it become 2? I don't know, shit. I know it's going to be less than 1 because 10 to the first power is 10. You guys kind of follow a little bit? So I can't do either one of those separately, but what does this property here tell me I can do? I have the sum of 2 logs, same base. That's got to be the log of the product. 5 times 2. And what's 5 times 2? 10. And what's log base 10 of 10? 1. So I went from completely impossible for me to do, but because of the property, I can combine them and make something that's possible to do. So you can do the same thing if I had, let's say, log base 3 of 39 minus log base 3 of 13. Again, either one of these on their own, I can't do shit with them. What do you raise 3 to make it 39? I don't know, something more than 3, because 3 cubed is 27. I don't know. But when you subtract, what do you do with the insides? Divide them. Because when you subtract powers, you must have been dividing the things. So you can rewrite this as log base 3 of 39 over 13. And what's 39 divided by 13? Freaking 3, and the log base 3 of 3 is 1. So here, you guys try this one. What you got, Jeff? I don't know, Jeff, man. Before you go slamming any logs in the universe together, why exactly am I allowed to combine these 2 logs? Because the bases are the same. If the bases were different, the properties are like, I don't know what the hell to do with that shit. But the bases are the same, so when I see a difference of logs, that's powers being subtracted. When do I subtract powers? When I was dividing. You see how easy it is to remember. If you know the properties of powers, you know the properties of logs. Period. So this will become log base 2 of 20 over 5. So log base 2 of 4. 2, because 2 squared is 4. Yes, ma'am.
Are we going to have to know if the base is different?
No. I mean, it's if the base is different, there might be some little weird things you could do, but normally there's nothing you can really do. So, I mean, I'm not going to do that to you because that would be really evil, but just make sure you understand you're looking for like bases first before you do anything. So, of course, here you're adding powers. When you add powers, when you multiply like bases, 9 times 16 is 144, and so this is going to be 2, because 12 squared is 144. I know people start to divide. We already have a division symbol. So this symbol must mean something different. Right? We didn't just go, yeah, let's change the square roots of the division symbol to log. No, we didn't do that. This is a brand new thing. Alright, so here's the last property. And then I've got a handout. On one side, it's a summary with examples of everything we did today. And on the other side is your actual homework for this. So hopefully you weren't too excited that you wouldn't have homework. You know me better than that. Here's the last property that we'll talk about. And let me build up to it. So let's say log base b of a to the m. Bam. I like it. Now what does a to the m mean? A to the nth power. Makes me sound like I have a lisp. What's a to the nth power? Ruth Chris Steakhouse. Okay, what is a to the n power? If I said, figure out by hand what 13 to the 5th power is, what would you start doing? You would do 13, multiply by 13, get an answer, times 13 again. So what does it mean? It means 13 to the 5th power is how many 13s? 5. That's correct. So what does a to the nth power mean? It means how many a's? Multiplying how many? M of them. Okay. So there's m a's here, right? Here, let me do this for a second. Let's put some numbers in here. So what's log base b of a cubed mean? It means log base b of a times a times a. Right? I have a property that tells me what to do when there's a product inside. The log of the product is the sum of the log. So wouldn't this be log base b of a plus log base b of a plus log base b of a? And what is something added to itself 3 times? What is x plus x plus x? 3x. So what's log base b of a plus log base b of a plus log base b of a? 3 log base b of a. If that would have been a 4, I would have written 4 of these, and then there would have been a 4 here. So if that's an m, what's going to be there? Freaking m, because how many of these am I going to write? M of them. So this is m log b a. So look what happens. The log of something to a power, the power just comes down. And also, I want you to realize, what do I do with powers when I raise something with a power to a power? What do I do with these? Multiply them. So isn't that power is going to multiply by that power. So again, it's the same property as properties of powers. Why? Because logs are frickin' powers. That's why. So this property is what helps us solve problems Here, don't even write this down. I have to show you this, but don't even write this down. This is not anything I'm going to ask you to do on your own. So if I had this, 7 to the x equals 11. What? Anybody have the calculator out? Do you have a power that looks like it's related to what we're talking about right now? I mean, a button? Yes, you do.
Somewhere on here, I see it.
Yes, you do. What button is it? It's the log button. It's a log button. It's above another button. It's like you have the shift key to get to it. And when I just see a log by itself, it's log base 10. Why is log base 10? So like when I see a root symbol by itself, what do I know is here? A 2, because it's the most used root. So when I see a log without a base written, it's base 10, because it's the most used base. Why is that the most used base? Because our number system is based on 10, maybe. So they said, let's not even write 10. Let's save some time. Right? Math people were lazy, or frugal with their time. So if I just take the log base 10 of both sides, whatever I do to one side, I have to do the other side. What can I now do with this x? Based on the property we just learned about, it could freaking come down. So the whole problem with solving this equation is my x is stuck up here. Before today, we had no way to get it down. So if the x was stuck underneath, what would I do? I would just multiply it so it would get out of there. It would come back up so I could move it around. You guys kind of understand what I'm saying? I have to have a way to get it free from where it's stuck. I didn't have a way to get this free. Now I do. It would come down. So x would be then divided by log 7. Alright, do this quickly because I'm not going to make you do that. But that's the most useful property, because I can immediately start solving anything with unlike bases. Like somebody said, like we said, it's just, I was making 9 and 27 work with each other. What if it was freaking 7 and 11? I'm screwed. Well, now I can use that. And I can plug that in the calculator, get a number for it, and sleep easier, I guess. Maybe. Weird shit. So this you're not responsible for. I couldn't stop myself. I had to show you this. Okay, let me give you this, and let me let you look it over for a minute, and then I'm going to let you guys out of here early. Hopefully you understand that also lets me out early, so not completely finished. No, it's due by the final. Just like always, the day of the next test, the next test is the final. But you can certainly turn it in early. Never a problem with that. So I try to capture everything we talked about today, and examples of each. At the very bottom are examples of the properties we just talked about. Now on the back is your homework for this stuff. Not too bad. Hopefully. Don't let logs be bad. Don't let logs beat you down. We created logs. We're the humans. And that's it, unless you have a question about something on there.
Wait, no, you just add the
Beautiful.
two, right?
Yeah, they have like bases, you just add the powers.
You just keep it as 4 or as 6?
Ah, I got you. Really good question. If I've got this, 5, let's say I got 5 to the x times 5 to the x plus 1. What do you do with the powers?
You add them.
Now, if you put down, this is wrong. If you say this, x plus 1 is 2x plus 1. What's wrong with that, Jeff? Because I don't see any 25s. I don't see any 25s. How did you get 2x plus 1 of them? If I don't see any of them, I have 2x plus 1 what's? 5s. So I'm just keeping track. Now it's right. I'm just keeping track of how many 5s I've got. Here I've got x of them. Here I've got x plus 1 of them. So how many 5s do I have now? 2x plus 1 of them. The base doesn't change. We know that already. What's x squared times x cubed? X to the 5th. Did the x change? Of course not, because we're keeping track. 2x's, 3x's, so there's 5x's. So many 5s, so many 5s, so there's so many 5s. The base won't change. Of course not. I like. Good question, though. Sweet. That's it.